This video develops the previous video to show how de Moivre's theorem can be used to find the roots for high-order roots like third order, fourth order, and so on. So the previous video showed how the square root could be thought of or obtained through an inverse operation. That is, think of an x such that x squared equals a. Now this video will show that using the same sort of technique or thinking can be used to find higher order roots such as Q roots, fourth roots, fifth roots, and so on. And it is this thinking that's critical that underpins the application of de Moivre's theorem for root computation. Some background then, just to remind you that if you multiply two complex numbers together, then, as you'll see at the bottom here, I've multiplied this complex number by this one, then the modulus of the product is the product of the moduli, and the phase of the product is the sum of the phases, and that's a result we use later on. Now, where does de Moivre's theorem come in? We're going to use this multiplying two complex numbers rule. So you'll notice what I've done here is I've multiplied a complex number re to the I theta by itself, and therefore the product has given me a moduli r squared, and the phase has become 2 theta. What about if I multiply a number by itself twice? In other words, I cube it. Then what do you notice? I get the modulus cubed, r cubed, and then e to the I, 3 theta. I get 3 times the phase. What if I do that n times? So I take a complex number and I put it to the power n. Well, hopefully it's obvious. The modulus is going to be r to the power n, and the phase is going to be n theta. In other words, you just multiply the phase by n. Now we're going to use this result hereafter and take it for granted. What about cube roots then? First, it's important to understand what do we mean when we use the term cube root. And this is a typical notation. You can see I want the cube root of 64 or the cube root of 125. I think it's easier to think of this using an inverse sort of operations. So define the cube root to be a value x such that x cubed equals the original number. So in other words, instead of trying to solve for the cube root of 64 equals x, I'm going to say try and find an x such that when you cube it, you get 64. And clearly I can see that 4 times 4 times 4 gives me 64, so the cube root is 4. If I wanted to get the cube root of 125, I say think of an x such that when I cube it, I get 125. And you can see clearly if I do 5 times 5 times 5, I get 125. So the cube root is 5. Now, it's easy to say, think of a number that if cubed gives you the result you need. So here's another example. Find the cube root of 512. So what I'm suggesting is you use this equation here. X cubed equals 512 and not this equation here. So we can use an iteration. We could say let's try x equals 7. Well, if I do 7 times 7 times 7, now without multiplying it out, it's pretty obvious that that's not going to give you 512. But I could try 8 times 8 times 8, and you should be able to fairly quickly show that that does equal 512. So 8 is your cube root. However, here's the interesting thing. Shouldn't there be 3 solutions? I've asked for a cube root, and I've sort of got this feeling there should be 3 solutions. And indeed, you can see that because equivalently, I could have written this problem as x cubed minus 512 equals 0. So it's a cubic polynomial, and we know that cubic polynomials have 3 roots. So where are the other 2 roots, and how am I going to find them? So our suggestion is, as in the previous video, the easiest technique for locating all 3 solutions, not just one, is to use complex numbers in exponential form. So that's what we're going to do here. So first of all, postulate that the root you want, the solution, is w equals r e to the I theta. And then I can write out that w cubed is r cubed e to the 3 I theta. So that's step number 1. Now, we said the cube root problem is equivalent to writing this. So instead of finding w equals the cube root of a. I'm not going to do it that way. I'm going to do w cubed equals a. Now I've already rewritten w in exponential form, so I can now rewrite this problem as find r and theta such that r cubed e to the 3i theta equals a. So this is the problem that I'm going to try and solve, and it's somewhat easier. So here we go. Now the next thing to do is write the original number also in exponential form, and then do a match. So you'll notice my original number was a. Now I'm assuming for now that this is real. Okay, so therefore I'm going to write a equals a e to the i0, the phase is 0, or a e to the I 2 pi, because 2 pi essentially puts you back on the real axis, or a e to the I 4 pi, because again 4 pi puts you back on the real axis. So the first thing, write the original number in exponential form, which is what I've done here. And now I can equate both sides of the equation. Okay, so match the modulus and the argument for each side. So I want to solve w cubed equals a. I've got that w cubed is this, r cubed, e to the 3i theta, and I've got that a is either a e to the i0, or a e to the I 2 pi, or a e to the I 4 pi, and so on. And what you can see, therefore, is if I equate the moduli, I get r cubed equals a, and if I equate the phases, I get 3 theta equals 0, or 2 pi, or 4 pi, or so on. So there's the summary. I get r cubed equals a, and 3 theta equals 0, or 2 pi, or 4 pi, or 6 pi, or 8 pi, and so on. And there we have the answer, therefore. So r is the cube root of a, where a is a positive number, and theta is going to be 0, or 2 pi by 3, or 4 pi by 3, or 6 pi by 3, and so on. Now let's put these answers in an Argand diagram just to see what they look like. So I'm going to do w equals the cube root of 27. So in essence, all I've done here is I've said that a equals 27. So if I use the previous page working, then you find that the solutions are 3 e to the i0, 3 e to the I 2 pi by 3, or 3 e to the I 4 pi by 3. Now you'll notice, first of all, they've all got a modulus of 3. So what I'm going to do is mark out where 3 is, just so that I can see. And although it's not going to be a brilliant sketch, I'm going to do a circle with a radius of 3, so it's not very easy to draw on the screen. So all my solutions must lie on that circle. Next, what I'm going to do is look at the phase. The first one has a phase at 0, so I have a root here. The second one has a phase at 2 pi by 3, or 120 degrees. So if I draw a 120 degree line, well, that's 120 degrees, then the solution must be there. The second one has a phase 240 degrees, or equivalently minus 120. So the other solution is there. So you can now see where each of the 3 roots lie. Now you'll notice there's an interesting observation here. You'll notice there's 120 degrees between each of the roots. There is a symmetry. They all have the same modulus and have the same angle between them. And that's not really surprising. The other thing you'll notice is obviously if you multiply them together 3 times, you get what you expect. So if I do 3e to the i0 and cube it, then clearly you get 27. That's the easy one, because the e to the i0 is just 1. So I'll get rid of that one. But let's just do one of the others. What if I do 3e to the I 2 pi by 3 and multiply it by itself 3 times? E to the I 2 pi by 3, 3e to the I 2 pi by 3, and what do you notice? You see you get 27 e to the I 2 pi. It brings you back to the real axis, which is just what you expect. So 3 lots of 120 degrees brings you back to 360 degrees. Or 3 lots of minus 120 degrees brings you back to minus 360 degrees, which is the real axis. Okay, just a reminder then of the links to a polynomial. You remember that solving w cubed equals 27 is equivalent to solving w cubed minus 27 equals 0. So in other words, factorizing a polynomial. Now we've just worked out what these roots are, so I can, if I want, now plug them in. And a proof for you to do is prove that w minus root 1, there it is, 3e to the I 0, times w minus root 2 times w minus root 3 equals w cubed minus 27. Multiply that out longhand and prove to yourself that it does indeed work. You shouldn't find it too difficult, but just a hint for you to make it a little bit easier. If you take these two factors here, which are the two factors which have complex roots, and that's what I've done down here. You see the two factors with complex roots. If you multiply those two together first, then what you get is this down here. Now why is that useful? Because at the end you'll see I get an e to the I 2 pi by 3 times e to the minus I 2 pi by 3. So those two angles are going to cancel out, and you'll just get a plus 9. Similarly, you'll look here, these two exponentials are complex conjugates, and you'll realize that when you add complex conjugates together, you just get left with a positive number. So when you add these two together, you'll find you just end up with 1. But I'll let you try that yourself, just to make sure that, oh sorry, I should have put minus 1, not plus 1. You try that yourself, just to prove that it works. Okay, what about higher order roots and roots of complex numbers? So we've done roots of positive numbers, roots of negative numbers, but what about roots of complex numbers? Now, let's say for example you wanted to solve the fifth root of b and put that in y. And what I'm suggesting is easier to solve y to the 5 equals b. I find a value of y such that when you put it to the fifth power you get b. Or you can treat it as a polynomial problem, which we're not really doing today. What if you wanted the 8th root of a, and you were going to call that z? Well, it's easier to solve z to the power 8 equals a. Find a value z, such that when you put it to the 8th power, you get a. And you could put that in polynomial form if you wanted, which gives you z to the 8 minus a equals 0. Now, hereafter, here's the key difference from the earlier in these videos. We're going to assume that b and a are not real anymore. We're going to put complex numbers in and show that it doesn't make any difference to the approach that you use. So here's an example. W equals the fourth root of minus 256. Or in other words, using this sort of inverse problem approach, we're going to try and solve w to the 4 equals minus 256. The first step, as ever, write w in exponential form. There it is, w equals r e to the I theta, and write minus 256 in exponential form. So there we have minus 256 equals 256 e to the I pi, or 256 e to the I 3 pi, or 256 e to the I 5 pi, and so on. Next, match the modulus and argument for each side. So, what we've got is r to the 4 has got to be 256, and 4i theta has got to be I pi, or I 3 pi, or I 5 pi, and so on. So what we get, there we go, r to the 4 is 256, and 4 theta has got to be pi, or 3 pi, or 5 pi, or 7 pi, and so on. And if I finally reduce that, you'll notice that r is clearly 4, and theta is clearly pi by 4, or 3 pi by 4, and so on. Then your solution, w equals r e to the I theta, has got to be 4 e to the I pi by 4, or 4 e to the I 3 pi by 4, or 4 e to the I 5 pi by 4, or 4 e to the I 7 pi by 4. And if you try and calculate any more, you find that you end up back with the original solutions, so you're no longer finding new solutions. Let's put these then on an Argand diagram to see what they look like. So first of all, 4e to the I pi by 4. Well, pi by 4 is 45 degrees. Okay, now I'm going to mark my circle of radius 4, because you'll notice all of these numbers. Okay, I'm not very good at drawing circles, but you'll find all of these numbers lie with a modulus of 4. So they're all going to lie on that circle. So 4e to the I pi by 4 has got to be there, at 45 degrees. 4e to the I 3 pi by 4 is there. 4e to the I 5 pi by 4 is there, and 7 pi by 4 is there. So what do you notice about these solutions? There's 90 degrees between each of them. There is a symmetry. They have the same modulus, and they all have 90 degrees between them. They're equispaced, and that's quite important observation. Now, a final example, just to really test you. Can you cope with this? I want the sixth root of 4096 times 1 plus I root 3 over 2. So how are you going to go about this? Well, of course, the first thing is to write it as an inverse sort of problem. So I'm going to say, I want to solve w to the power 6 equals 4096 times 1 plus I root 3 over 2. Now, it may not be obvious to you by inspection, but you can check. But 1 plus I root 3 over 2 can be written as e to the I pi by 3. So I've already written that number in exponential form. And the other thing that you may not realize, so I'll write it here for you, is 4096 is 4 to the power 6. And I've done that to make the numbers easy. Oops. So, what am I going to do next? So if I write w equals r e to the I theta, then w to the 6 is r to the 6 e to the I times 6 theta. So what I'm trying to solve is the following. That r to the 6 e to the I 6 theta equals 4 to the 6, that's the 4096, times e to the I pi by 3. So that's solution 1. However, equally, I could have said, or 4 to the 6 times e to the I into pi by 3 plus 2 pi, because pi by 3 plus 2 pi brings me back to the same phase, so it's the same complex number. Or, I could have had 4 to the 6 e to the I pi by 3 plus 4 pi, because again, 4 pi brings me around twice, brings me back to the same place. And indeed, I can do another one, or 4 to the 6 e to the I pi by 3 plus 6 pi, and so on. Now, I'm going to need 6 of these, because I know I'm looking for 6 roots, so I need 6 different solutions before I'm finished. So when we solve this, hopefully it's fairly obvious that you've got r equals 4, and you've also got 6 theta equals pi by 3, or pi by 3 plus 2 pi, or pi by 3 plus 4 pi, or pi by 3 plus 6 pi, and so on. And therefore, if I solve for theta, you've got pi by 18, or pi by 18 plus pi by 3, or pi by 18 plus 2 pi by 3, or pi by 18 plus pi, and so on. So what I'm going to do now is put these in an Argand diagram, because when you see the picture, the pattern is obvious. So first of all, we said the radius was 4. So let's do our circle as well as we can, just to make sure that we get these in roughly the right place. I should learn to draw better circles, but anyway, so be it. Now, the first one had an angle pi by 18, which is about 10 degrees. So that's going to be down there, and I'll mark that so you can see it's about 10 degrees, or pi by 18 in radians. The next one was at pi by 18 plus pi by 3. Now pi by 3 is 60 degrees, so that's going to take you to an overall argument up here of 70 degrees, but the key thing is the jump was 60 degrees. So you're going to go to there. If you looked at the next one, you'll see the next jump was another 60 degrees, but before I do that, I'm going to recognize a bit of symmetry here, so I can get them in roughly the right place, and what you'll find is you get this. Oh, I've done that wrong. Let's always happens when you're trying to do things on a screen. What I need to do is mark here that you've got a 60-degree gap between each of the roots. You'll have seen that on the previous page. We went plus pi by 3, plus 2 pi by 3, plus 3 pi by 3, and so on. So you're moving up 60 degrees each time. So you'll notice that sort of symmetry or pattern in the roots. They're all 60 degrees apart, and they've all got the same radius. And the only thing that changes as you change this complex number under the root expression is where you start from. And here, I had to start from 10 degrees. So some conclusions. This video has shown how one can solve for the nth roots of a complex number by using an inverse approach. So you think of a number that when you put to the power n, gives you the result you need. Now, multiplying complex numbers multiple times is straightforward, and that's essentially what de Moivre's theorem does for you. Okay, and this is used implicitly in roots computations. And one thing you need to note is that all the roots have the same modulus, and the phases are separated equally. So 180 degrees separation if you're looking for square roots, 120 degrees separation if you're looking for 3 roots. And you're wondering where that's come from. Well, 180 is 360 over 2. 120 is 360 over 3. And what if you have 4 roots? You're looking for the 4th roots. Well, you get 90, because that's 360 over 4. And if you had 5 roots, what do you think you would get? Well, you're going to do 360 over 5, so you'll see the roots are separated by 72 degrees, and so on.